So my name is Alberto Ceselli, still from Optela Unimi. So let me share also my views on how possibly machine learning and operations research can interact. So, in my opinion, that's what I see. There are three ways in which they can interact. So maybe in a machine learning application, you have sub-problems which are optimization problems. You already know how to solve them. But maybe there are more modern techniques speeding up the computation. So not really changing the result, just engineering, right? So speeding up and nothing else. Second way is, well, replacing some heuristics that you normally use with some exact methods that 20 years ago was not working for computational reasons. But right now might even work. I don't know, I see, for instance, that in R libraries for clustering, say k-means, it's still using a kind of alternating heuristic. So cluster, then choose the center, then cluster, then choose the centers, right? Which is very dependent on the number of iterations that you give. For instance, this is an example of a problem that may be modeled as an integer optimization one, and that is providing you good solutions and also help you in answering the possible question, okay, I get strange results. Is because of my model or because of the algorithm solving my model? Third thing is, well, solving prescriptive analytical questions. So not really questions in which you have data and you wish to find out something unknown from data, but to answer precise questions that you have in mind. Okay? So you already know very well the question that you like to answer. And you just wish to, I mean, give shape to data and models to answer these questions. Okay? And that's what I'm about to talk. So, and prescriptive analytics for a nice application. Okay? Having said this, all these three directions help us in publish more papers. That's the ultimate goal. I admit it. Okay, very well. So our application was about mobile edge computing. Okay, so this is. So this is how I understood mobile edge computing. So in legacy networks supporting the connectivity of mobile users to the internet, you have this kind of structure. So mobile users connect to the network by means of antennas, access points, right? Then you have some kind of network functions which are implemented typically by hardware, placed at some points in these networks, okay? This core network. And then you have possibly application servers which are placed in remote locations and connected through the internet, okay? Mobile edge computing relies in the virtualization of everything, okay? So, or in the softwareization, as my colleagues in networking call it. So, all these network functions, as well as the application servers, are instead implemented by software, so by programs running on servers which are placed at some level of this network, typically much nearer to the access points than in the previous architectures, right? So, okay, one may say, okay, so what's the point? The point is that this is a very, I mean, protocol-centric view of networking, while this is a very data-centric view of networking. Because by means of data, we can have control of these software components and make them work really well or really bad. well, stop me if you have questions, comments, please. Okay? Very well. So, in particular, there are two types of services provided given to the users. So that given by application servers, because okay, in a virtualization scenario, say also the terminals, so the phones of the mobile users may become virtual in the sense that the real computation is performed in the remote server by offloading, and then what the user gets is a streaming of the results. Okay, so it might be possible to assign to each mobile user a virtual machine running in a remote server. The other type of virtualization is that of the network functions. Okay? Very well. So the association of mobile user to virtual machines is 1-to-1. So user to virtual machine. Well, the association of network functions to users is through the access points. So access points are assigned to particular facilities for running these network functions. Okay. Very well. So what we would like to do is, well, these facilities have devices that have limited capacity, and well, people connecting to these facilities use resources on these devices, right? So we would like to provide the best possible quality of service to the users, trying to not exceed the resource limit which is available on these facilities. That's our aim. Okay? That's what we try to do. For doing this, we can perform some kind of load balancing. That is, at some point in time, I may assign some access points to some facilities, because I know that here, for instance, the demand is much higher than in these two. And therefore, I may be interested in merging these two in the same facility and splitting this one. But maybe, since demand, users are changing in time, demand is changing in time, I might be interested in changing the assignment over time. Okay? Good. In such a scenario, I have two kinds of costs. A cost related to the users. So user usually always likes to be connected to the nearest facility because it has lower latency, better service, say. Well, for the system would like to never see migrations, so never see switches, because a switch requires the transfer of huge amounts of data. So it's heavy for the network. Okay? Good. Our aim is to find optimal assignments of access points to Mac facilities over time. That is, those minimizing a combination of user level of service and system load. In principle, one may do this, in a reactive fashion. So one may simply run the system, observe the load on the facilities, and when the load on a facility is starting to reach a critical level, one may switch, right? That's what we call a reactive decision. But besides these reactive decisions that one can always take, we wish also to take proactive decisions in a tactical way. So to prevent the approaching of critical resource usage, okay? By designing switching patterns, so assignment patterns, to be applied independently on the particular level of load of the facilities at a certain point in time, okay? But decided a priori, okay? Good. So we try to use for taking these tactical proactive decisions this kind of data-driven architecture. So we assume to have our mobile edge computing network. We have an orchestrator running this network, so a software entity managing all these software virtual functions. We have logs, mainly about the demand of services in the network over time. And we basically employ two components for obtaining these optimal, proactive, tactical decisions. So a pre-processing component and an optimization component. Okay? So in the pre-processing component, we basically try to map an optimization problem that would be in an infinite horizon, because, well, proactive decisions may be taken tomorrow, in 2 days, 3 days, 1 month, 2 months, and so on, into an optimization problem instead on a finite horizon, a finite number of temporal slots in which deciding to change decisions, deciding to change assignments might make sense. Okay? So in this preprocessing component, we employ clustering. So first of all, time series analysis to understand if periodicity in demand values exist, and clustering, spatiotemporal clustering, to understand if time windows exist in which the status of the demand on the network is more or less constant, and therefore changing decisions do not make sense. Okay? That's, for instance, a result that we get by analyzing the demand of users in a real network. So same color means same cluster produced by our preprocessing tool. Okay, so this indeed, as you can see, every day basically has the same pattern. So different colors are different time windows, except Saturday and Sunday, which make a difference, right? So our idea is that by choosing an assignment pattern for each of these clusters and repeating it over time, one might get good proactive decisions. Okay? Good. Very well. That's not the end of the tale, because once you define these time slots, a decision problem remains. A hard decision problem remains. That is, good, how I assign access points to the MEC facilities. Access points have demands. Facilities have capacities, right? I have an assignment cost. I have a switching cost. This is an optimization problem over a finite horizon, finite number of slots, right? And these I can model using mathematical programming that Andrea was talking about. So this nasty model with lots of equalities, inequalities, variables, data, as an example of a mathematical program. Okay? Might be scary, but it's a problem having a polynomial number of variables and a polynomial number of constraints. This is an example of a problem that if you succeed in modeling like that, can be solved by black box optimizers like, I want to say Cplex again, I would say Robin, right? Or Express, or Skip, okay? So, if you model a problem like that, with general purpose tools, you have lots of chances to get an optimal solution in a reasonable time. Okay? Good. Questions? Comments? Great. That's almost over. Because yes, please.
You try to apply this method in other fields, like financial time series, or because it's all about time series, basically, right? Networking problems are a little bit further away from my personal.
Yeah.
But for instance, time series is very interesting. So my curiosity whether it was already applied by you in some other field.
No other fields. That was specific to that application. But I should say that, okay, so these are the two ingredients, right? So this is custom. This needs to be changed application by application. So the model that we designed, as I said in the beginning, so helps in answering a very precise question. So we had the very precise question in mind at the beginning. It's something that is making the difference. However, the remaining of the architecture may be. So in general, that's something that you can try if you have decisions over an potentially infinite horizon, and then you use, I guess, your expertise to find regularities, periodicity, and so on and so forth, to reduce it to a finite horizon, and then optimize. This seems to be promising as a conjecture. Okay? Good. So now what I would like to show you is some results that we got. Okay, so we tried to run some experiments on real data. So we had real network data over the cities of Lyon and Paris. They have this kind of number of base stations. You may be hard to see, but I mean this is already a spatial aggregation of base stations in Paris. We used as we focused on a specific mobile service, Facebook. So we had real Facebook traffic over 2 months. It's 16 weeks, 4 months. Okay, given by a mobile operator in France. Good. So what we did was, okay, let's train. Let me go here just. Great. So we had these 16 weeks. So we took the first 4 weeks. We performed some aggregation of data over these 4 weeks, and this gave us some, say, very simple data about expected demand in each time slot. We really took the average over the 4 weeks, or the median. These were the two checks that we did, and this became data for the optimization algorithm. Then the optimization algorithm produced solutions, and we applied blindly these solutions to the remaining 12 weeks. So many things can happen. So either you optimize very well on the first four weeks, but on the remaining 12 weeks you don't know anything. So the cost might not be what you're expecting, but also the capacity, because in the first 4 weeks we guarantee the capacity to be respected, but on the remaining 12 you don't know anything, right? So we measure a posteriori what happened. Well, for instance, this is execution time. I mean, this was reasonable both with the general purpose solvers and with a special purpose algorithm that we designed for the problem. That's not a problem. Okay. For what concerns the cost, what you get is, okay, well, you don't have really other simple options for taking these decisions besides the pure reactive approach, and so no periodicity, right? So okay, so that's the reactive benchmark, and this is cost. Okay, so this is the cost slack with respect to an optimal solution. So the reactive approach gave, say, as a median cost, say 19% worsening. Okay, while this was our result, so goes from very few percentage points if time granularity is chosen very fine to up to 9% when granularity is more coarse. Okay, and same for capacity violation. Similarly, so let me take this. So optimizing a lot is not really causing over usage of specific facilities. So capacity violation was very low in any case. Okay. So that's what we understood from our application. Well, first thing that we understood that, okay, in the context of networking, data-driven approaches are very promising. That's an example. The ingredient number one for the success of this method was the pre-processing tool. So moving from infinite horizon to a finite one. Ingredient number two is using mathematical programming for optimizing over even simple forecasting to produce decision patterns. Ingredient number three is, okay, you need to produce solutions that then are easy to be implemented in practice. Do not require lots of adaptation. And I guess that's it. I would be glad to answer questions, comments. Yes, please.
I have 2 questions.
Yes.
Not specific about the application, general
yes.
operations transaction. Let's say I want to industrialize a solution like these or like other optimization problems, but I don't want to have the complexity of implementing from scratch. Are there some provider of optimization as a service, cloud provider or whatever?
You mean for the solver or
for solving? Let's say I want to deploy some algorithm. I don't want to deal with computational power, choosing the best solver, the best platform, or linking to complex APIs. You know if there are provider of optimization as a service, like cloud providers?
Yeah, IBM is doing all this stuff.
IBM?
Yeah, I think so.
Second question.
Yes.
If I understood correctly, all these optimizations are batch algorithms. So you define constraints, give a set of data, and then get a solution. Are there like online algorithms where you set constraints, set the model, and give the data point one at a time and update online the best solution?
There are, but I believe they are different in nature. So look at this model, right? So this model, I didn't discuss about it, but one of the summation is over time slots, right? So you add more time slot, you enlarge this set, you need to introduce further variables. So nobody forbids to start from the existing solution, add more variables, and optimize with a warm start from the previous solution. So in principle, you can use it. But I guess it's not what you want in an online setting. You are more interested in, say, competitive policies, right? Mm-hmm. So very simple policies that maybe give you probabilistic guarantees. So over-optimization is maybe not what you really want, right? So in principle, you can. I'm not sure it's the best choice for every application, especially in an online setting. We have online optimization techniques, but are different in nature. Yes?
Why some data are not used for testing the model? I mean, just use all data for just train the model. Also say
no. Of this, sorry, maybe I was not clear about it. Over this 16 weeks.
Yeah.
So we took 4 for training and 12 for testing.
Okay, was meaning the first 4 just for give
first 4 for feeding this data with the model to the model. Mm-hmm. Then you optimize over this data. Okay. Then you discard these 4 weeks, discard the existing data. You just pick the solution given by this model and apply to the remaining 12 weeks.
For testing.
For testing.
Okay.
And the results you have got are on the testing.
Okay.
But why the testing period the double of the training? Because usually you try to use as much data as you can as for training. Maybe because you don't expect to get much more enlarging in the training set.
Yes, that's a point. So so one of the that's also related to the application, because my colleagues in networking said, okay, but the main critical point can be fluctuations of demand over the weeks. Okay. So if you train on, say, 2/3 of the data set and just test on 1/3, the main criticism would be, yes, of course, but okay, you have very little fluctuations in very few weeks of data, right? So we try to have the test set as large as possible. More than 12, well, we didn't have enough regularities to feed this data. But that was the meaning.
Potentially you would also have fluctuation over the year. But they would require a lot.
That's true. But so it would indeed be interesting to have even more data, yes. But that's the reason, yes. Yes.
This approach is a bit similar to orchestration of clusters from software like Mesosphere or something like, because if for example, if you have many Docker and these Docker are not inside a specific node, you have many nodes. So it orchestrates, and if a Docker go down, it publish it on a random node based on the resources. But the interesting thing is that publish the Docker on optimization, its own optimization. But if you want to, you can put your logic, your own logic with the constraints, with your based on your. It is similar to. I don't know if it is a similar approach or an approach used for this kind of orchestration of the resources.
Yeah, I guess they use it a lot. But as far as I know, and my colleague told me, I'm not the networking expert of the band, but still. Reactive decisions are very popular, even by constraint like telling, okay, when you see demand approaching 90%, so you have a constraint top 90% of the available resources, then do something. Reactive decisions are very, very popular. Proactive ones are less popular and less intuitive, because if everything is going well, why would you mind to switch people and change assignments and might do migrations beforehand? But this seems to experimentally be fruitful. Great. So, if there are no other questions, I would